Hello everyone, welcome to CS240's Lab 4 video, and in this lab we will be talking about recursion and how to code in assembly, how to code recursion in assembly. And let's get on it. In task 1, we required you guys to have a look at this following C code, which is in high level. And translate it into very simple CPU assembly. And you can see that in our main code, we basically have, let me, yeah, we basically have just two numbers, and we are basically calculating the power of 3, and I mean 3 over 5 basically. And how we calculate it is basically using this function right here, which is power 3 and 5. And in the method itself, which is here, you can see that if the exponential is 0, it just returns 1. But if it is not, it's returning base times, which is in this example 3 times power 3 over 4, 3 to the 4. So it's basically doing recursion over and over again until it gets to 0 exponential and gets back up from there. And in the assembly code, we wanted you guys to have x and y in 200 and 201. Basically, just write 200 semicolon and then 3, and then also 201 semicolon 5, and then the results should be saved in 500 after your program finishes, like before go to end, basically. For the method part, for the recursion part, the base parameter should be in 300, and you need to keep these values, the exponential value, the return value, and the return address value in 600, 601, and 602. And according to the recursion, you need to use more of these values. For example, keep exponential here, return value here, and return address here. But if you need to do recursion like this, you need to keep, for example, exponential -1 in 603, and then also return value of this method and this part in 604. Just basically added 3 to this one, since we have 3 values that should be used in each method. Well, 4, but it doesn't change in recursion. So since we have 3 values that change in our recursion, we need 3 different data locations. And since it's a recursive function, we need more of these 3 data groups. For example, if you are calculating 3 to the 5, you need to save 3 to address 300, and then 5 to address 600. And since 3 to the 5 will be 243, it should in the end be saved here, and then you're going to be saving it back to here before your program finishes. And the return address should be where you are saving the result to 500 basically. But since 3 to the 5 in 3 to the 5 function, we are going to not be doing this part, it's going to do this part, and it will call power 3 to the 4. So since it's doing recursion, 4 will be saved in 603, and then the return value of that will eventually be saved in 604, and the return address should, which is where you are going to be doing the multiplication for this part, will be saved in 605. And then since 3 to the 4 is again making function iterate one more time, we're going to be calculating power 3 over 3, 3 to the 3. So again, 3 will be collected. 3 should be saved in 606. And let me see. And return value of that one, 3 to the 3, should eventually be recorded in 607. And then the return address of that, which will get back to multiplying this again, should be saved in 608. And basically, again, in 3 to the 3, you're going to be calculating 3 to 2, which will keep 2 in 609, and then the return value of that one in 610, and then 611, and so on, until it basically goes to 0, the exponential, and then it's rolled back up from the memory from then on. And let me also, the start of the function should be in 400. Basically, the power function should be starting from 400. Maybe I can show you in an easier form how the stack works for recursion. Let's see. Okay, I have the basic code of this power function here in Excel again. And basically, since we have 3 values which are going to start from 600, 601, and 602, and so on, and we are saving these values in these locations, we're going to call it a stack, and it's basically like an array. You can consider it to be an array, but every 3 elements is basically connected to each other. They are belonging to the iteration of the power function that they should be in. Basically, for the example, if we are calculating 3 to the 5, we should be saving 5 here before we even start the power function, and 3 is also going to be in base, basically. Save this, and maybe also do this. And the return value will eventually be here. We don't know what it is yet. It's going to be 243, but it's going to be calculated at the end of the function. And also the return address of the method will also be important here, because you need to get back to your, let me show you, main function, and then add your main function, basically. So you need to be able to get back to here from this method. And I'm not going to write it here, but maybe I'll just write main here so that you know that you'll need to return to your main function. When you write your low code and your assembly code, you will know which address you will need to return to, because you have already seen methods and how they work. Okay, so let me think how to explain this. Since this is an array, and you know that in arrays we usually have some index which we increase in iterations, and then maybe also decrease them, which is why we need an index to like check which iteration we are in and do our calculation accordingly. And we usually call that a pointer, because it's basically pointing to an array. So you usually call that a pointer. Let me write it whole, maybe, just so it's easier to understand. And since the address of stack 0 will be 600, maybe we can write 600 in the beginning, for the beginning. And what we need to do from this function is, if we start calculating 3 to the 5, since it's not going to go in here, it's going to be going into this part, and it's going to try to calculate power base exponential minus 1. So if you need to go into a function, you need to give it the parameters, the return value, return address, and return value, address, and the return address themselves. So we know that we are using a stack with 3 elements, like basically in the same iteration. So we know that this repeats over and over again for each iteration. And for this function, the base is the same. However, exponential minus 1 is going to be different. And since our exponential is 5, the new exponential will be 4. So you need to provide 4 here before you need to provide 4 to stack pointer plus 3, which is because these 3 elements are combined. And then you need to also provide the return address for it, which is the multiplication place where the multiplication is going to happen. So I'm just going to write mult here temporarily, and you will know where you need to put it in your assembly code eventually. And the return value is again going to be calculated when the method is finishing up. So I can't write anything here. And then since we are calculating 3 to the 4 in this one, we have already set up these values, and then we jump to the start of the power in low C or assembly. We are calculating 3 to the 4. So it's again going to here and trying to calculate 3 to the 3, which will make us put 3 here, provide 3 before we start our next iteration of the power function. And the return address will again be where the multiplication is going to happen. I hope this is clear enough for you guys. If it is not clear enough, you should be able to ask questions on Piazza privately or not privately. However, if you're going to be sharing your code, you need to share them privately. And then again, you can also ask us via email. Do not hesitate to contact us. Okay, and after this, maybe I should write a few more of these here to make it easier on us. And by the way, these addresses just increase one by one. And again, stack 0, 1, 2, 3, 4, 5, and so on. And in this iteration, we are calculating 3 to the 3. However, it will again need to calculate 3 to the 2. So we write 2, we provide 2 to the next power function iteration. And then the return address should again be where the multiplication is going to happen. I'm just writing mult here to shorten it, to make it easier on me. It's multiplication. And where we are calculating 3 to the 2, we need to again call our power function, and we will need to provide 1 and also the return address again. And in this 3 to the 1 function, we are going to call it again, and we need to provide 0 and the return address, which is going to be the multiplication address. And just a reminder that we have gone up to 617 already, and in this iteration, since 3 to the 0 will be going into this part, it will just return 1. So right here, right inside this if, we are going to be making this return value 1, basically, and then using this return address, we return to the previous iteration where the multiplication is supposed to happen. And since we have this value, we are going back to this iteration, by the way. Since we have this value from the next iteration, we multiply it with the base and we write 3. And then using the return address, we return to the previous iteration, which is like this. I mean, this is the memory part, but you can consider it like the code, basically. And since we have the returned value of 3 to the 1 is 3, and we multiply it by 3, we get 9. And then we get to the next iteration and the previous iteration. And since we have 9 and we are multiplying by 3, it's going to be 27. And we are again multiplying it by 3 in the previous iteration, which is going to make it 81. And then since we have 3 to the 4 here basically, we again multiply it with the base, and then we get to 243. And then using our return address right here, we return to the main code and save our return value to address 500, and then maybe end our code. Or if we needed to do something else, we could do that also. Okay, this is basically the basic version of it. So maybe I can also write 3 to the 4 here and 3 to the 1, 0. So just so that it is a little bit easier to understand maybe. And we haven't used these addresses actually. However, if we had a larger exponential here, for example, not 3 to the 5, but like 3 to the 10, 3 to the 20, 3 to the 30, we would be using these addresses as well. So you need to allocate, I mean, normally you need to allocate a very large memory for multiplication and powering Fibonacci or factorials and whatever. However, it shouldn't really be that big of a problem if you don't put anything after these addresses. Basically, just write your code before these addresses. And we have already asked you guys to start your power function in 400. So if you work in basically 400s, it should be fine, and it shouldn't be that long. So you're going to be fine. And the stack pointer in this method is very important because in this iteration, you're going to be working with stack pointer, which is going to be 600. However, if you're going to be going into another iteration and you're going to be using these addresses to work with, you need to increase your stack pointer by 3, or if you had any other parameters that you need to include in your stack, it could be some other value. For example, you had 5 parameters that you need to use, it should be increased by 5. However, in this example, it should be increased by 3. So I'm just going to write plus 3 and 603. Oh, let me see if I can change that. Okay, that's pretty enough. And since we're going to another iteration from this point on, we need to again change our stack pointer to this one, and then again to this one. And then also, it should be here, yes, 612, and then also here should be 650. I mean, this doesn't really have to be the exact way you do it, but it's much easier for you guys to do it this way. Um, okay, so when you get to this part, since you're not going to be going into another iteration, you will need to use this stack pointer, this address, to calculate your value, the return value, which is going to be 1. And you need to write to 616, which is going to be basically stack pointer plus 1. So maybe try and save that stack pointer to temporary value and then increase it by 1, and then using indirect copy functions, indirect copy operations, which we have in our vertical CPU. You can write one here, and then basically when you need to return to a previous iteration and the return address is saved in 617. Normally, I would suggest that, for example, you guys to write like this, which will return back to the multiplication. However, you in methods, usually you cannot know the return address, in at least recursive functions, you cannot know the return address off the top of your head. If you write 617 in previous iteration, this 617 value will not work. So you need to access this again indirectly, and you need to use your indirect CP functions, which could be CPI or CPII. I'm just going to write CPI for a temporary instruction. Basically, I don't know what you're going to use. You need to know already what you need to use, and maybe save that. Uh, Let me see. Okay, maybe save the value in six 617 to a temporary address. However, you need to get to that using your stack pointer again. However, it should be stack pointer plus 2. So basically, after, for example, you get your return value, you can increase this temporary value by 1, and then since you have already a temporary value, maybe I can try this way for the rest of stack pointer. If TMP0 was stack pointer plus 1, and then you add 1 to this again, so then basically you can get, since this TMP0 is going to be stack pointer plus 2 at this point, it's going to be 617. So you get the value, maybe it should actually, okay, I'm not entirely sure. It should be, I think it should still be an indirect function. You can check it out for yourself and do it accordingly. When you write your OC code, you can find out what you need to do. However, you can copy the value in 617, which is the mult label, basically, where multiplication should happen, to temporary 1, and then using a simple DZJI TMP1 and 0, you should be able to get back to your previous iteration. And basically, since you're going to be going back to the previous iteration, you need to be also able to change your stack pointer before you go to the previous iteration again. So what you basically need to do is, before you jump, you need to change your stack pointer, which is going to be decreased by 3. So you need to basically do stack pointer minus 3 before you jump. So when you do this, since you have 615, you're going to have 612. And then you can basically repeat this code here, and you're not going to need to rewrite this code in your very simple CPU code, it's just going to be written. You should be able to do the rest of this one, and then also again decrease the stack pointer by 3, which will result in 609, and then we're going to do the same over here again, and then also here again, and then here. And when you get to this one, you're going to have this decrease the stack pointer by 3, and since you have 600, you can get this return value here, and then multiply it with the base, and then save it here, and uh, then again, you need to use stack pointer to find out when you need to save it, and then save it there. And then also using stack pointer, you need to return to the return address. So basically, increasing by 3, decreasing by -3, and maybe increasing by 1 or maybe more will be required for you guys. So just as a hint for you, you could use, since in very simple CPU, our values are unsigned, and I think you should already know by now that unsigned numbers can also be basically read as signed numbers. And for example, if you had 8 zip, let me think, maybe numbers in hex, which should be something like 4 million. There should be 8 Fs here, and if we were to read this unsigned, it should be something like 4 million something. However, if you read this in a signed manner, or well, I could actually do that easily. Let's see, it's the decimal converter. If I have 8 Fs, it's going to be, when it's unsigned, it's going to be this number, which is 4,294, or 4,294,000,000, and so on. However, if it is a signed number, it's going to be -1. So just as a hint for you guys, you need to, you should save -1 or -3 or minus whatever numbers in the assembly code, just like an address that you keep, and maybe in the code for the next part, which is the Fibonacci code, you can see here, for example. Let me see, actually, am I sharing the right screen? Yes, I am. You can see here, for example, -3 is saved in this address, and -2 is saved here, and -1 is saved here, just so it is made easier for us. You could basically write 1 to some address using cd little I, and then negate it using basically 2 instructions you have already seen the previous lab. However, this is going to be much easier computation-wise, and it's going to make your life easier for you. So I would suggest you using that. And basically that's about it. And maybe we can check out the high-level code of power before we go on to the next part. I've already copied the functions here, and let's see. Okay, I've already written some basic textual pseudocodes for you guys to maybe try to understand how you should write your low C and then assembly. And I'm saying you should write a low C, however, this doesn't say you should write low C, but I would recommend you do it, because if you write in low C, you can very easily change your low C code to very simple CPU. And basically in your main code, you're going to have these 2 values saved in these locations, basically, like perhaps we do also here. Let me see. Oh, okay. In this one, we don't really have it saved in some location, but for example, um, let me see. Okay, we didn't save it to some other location, but this could be, for example, saved in address 70, and then we would use basically CP70. So since we want you guys to already have these values in these addresses, it's going to be like 70, but instead it's going to be 200 and 201. So save these values to the parameter addresses, which should be this and these also. In your main code, basically you need to provide the parameters to those addresses and then also provide the return address, and your return value will be there at the end of your code. And then you need to jump to the function, which is the starting point of this method or this function. I'm saying sometimes method, sometimes function, they are the same thing. I may switch from time to time. And then we need to also write where we are going to go back to. And I've just basically written back. This is like a label. It doesn't really matter what you write as a label or anything. I just wrote it temporarily. And then since this function will end and it will get back to here, and also back should be basically the return address. Here you should save the results, which is going to be in 601. You should save it to 500 and then end your code. You already know how to do most of these parts, if not all of them. And in your power function, basically, which is where which should be located at address 400, you need to check if this exponential value, which is going to be in 600, is 0, and if it is 0, you need to jump into some location which will return 1, which is basically here. And the return value in stack, since you're keeping a stack pointer, it shouldn't really be an issue. Stack pointer keeps the first address, so since the return value is the second one, you need to use stack pointer, but save it to stack pointer plus 1, basically. Set stack pointer plus 1 to the return value, which is 1. And then change your stack pointer, which is when you're in a recursive function, you need to when your recursion is end, you need to get back to your previous direction. So you need to change your stack pointer and decrease it by 3, basically. You remember this part, I hope. And then you need to return to the return address, which is going to be in the stack, in stack plus 2, stack pointer plus 2. And then since you return to this part, it should, if it is recursive, or rather if it is not recursive, if you're calculating 3 to the 0, it should basically, since stack pointer is going to be 600, and we are returning to stack pointer plus 2, which is going to be in this address, we're going to be going back to our main code. But if it is recursive, when this code finishes, it's basically going to get back to somewhere around here, probably. It's not exactly the most important part. You will learn how to do it when you write your code. And this is not the only way you can do it, by the way. I just basically wrote it this way to make it easier on you. And getting back to the else part in the code, you need to basically subtract 1 from exponential and save it to save the value to the next stack location, which is going to be stack pointer, which is 600 plus 3. So you need to save, for example, if we're calculating 3 to the 5, we're going to be saving 4 to 603 using the stack pointer. Make sure you do it using indirect copy. Um, and then we're going to provide a new return location, which should be in the stack pointer plus 2, or rather the next stack pointer, which should be the previous or the current stack pointer, which is 600. So it's going to be 600 plus 3, or let me see. Uh, the new stack pointer will be 600 plus 3, and the new return location will be 600 plus 3 plus 2. Um, and you need to save where the multiplication is going to be done in that address. And then you need to basically jump to the start of the power function for the next recursion. And uh, by the way, this exponential that I've written here is basically basically going to be in the address 600, or in the next situation it's going to be 603 or 606, 609, and so on. So make sure you get this value using stack pointer again. Okay, it's going to go back to here and then do this part again over and over again. However, when it will get to basically exponential being 0, it will go back to here and then it will roll back the code. And since we are going into power base exponential -1, we have already provided a new return location, which is going to be the multiplication place. After we get to this one and we get 1 as the result and we return, we go up to here basically, and then we get the result from the power, which is going to be in that stack pointer, the previous stack pointer plus 1. However, since we've already got -3 from the stack pointer, we need to basically get stack pointer plus 4. And you need to get the result from there. For example, if we're in this iteration, you need to use, since we have stack pointer as 612, we need to use +4. We need to add to that packet +4 to that to get this value and then multiply it with that. So get that result from there and then multiply it with the value in the stack. I've already chosen to basically save 3 before going into each iteration. For example, if I'm calculating 3 to the 5, I save 3 here and then jump my next iteration and save 3 here and then save 3 here and then save 3 here and save 3 here. And when I calculate 1 here, I'm going to go back up and multiply 3 and 1 and then do my job accordingly and then multiply this value here, the previous value should be here 3, and multiply with this 3 and then get 9 and then times 3, which is 27 and so on. Or you can just use base, which is just going to be there for you. You can multiply this result with base and then return to the return address stack, which is stack pointer plus 2. And I think that's pretty much about it for this code. I know I have talked a lot about it. I have gone over it a lot, but it's not going to be too difficult for you. It shouldn't be too difficult for you, especially since you have the next parts codes and you can edit that code to fit your own code. It's basically you can make use of these and understand how it works. Um, if you have any troubles about this part, you can write to us via email or on Fianza as well. Let me save that. I don't know what I changed. Okay, and I think I'm done about this part, basically. And again, you don't need to really do it like the way that I basically written, but it's basically very explanatory for you guys. It's going to be easy for you. This text basically that I've written is a lower level of this. However, it's again a high level because it's just language. It's not a programming thing. It's a pseudocode. You need to use multiple operations in operations in assembly to carry out these lines as well. These are not just one line stuff. Some of them are 3 lines, maybe 4 lines. I'm not entirely sure. But if you check out the next part's code, you will be fine. Okay, and I think we can move on to the next part. And just so you guys know, you need to just upload these two files, and you don't need to change the names of these files as well. Okay, in this part, you're going to be having a look at the Fibonacci low-level C code and then fill just these parts in the assembly code. You don't need to write the whole assembly. Okay, this is the high-level version. Maybe I'll also open up the assembly version and the low-level version here. Okay, so in the low-level version, we just basically have some addresses saved already, just so you guys don't find it too difficult. And in the okay, this is basically also a typo. I must have ordered to fix that. Okay, in this code we have our main function. It doesn't matter if this is above or below in C basically, but in some other languages it has to be above the main function, or sometimes it basically needed to be below. I'm not entirely sure about all languages. For C, it doesn't really matter. In our main code, we have I as E, A as 2, and we are calculating uh, Fibonacci 2, and I'm sure you're all familiar with the Fibonacci series. I'm not going to go over it. You can maybe watch some video online to understand what it is if you don't know. So when we calculate Fibonacci 2, we go in this method and then see that since it is 2, 2 is not less than 1, so it's going to go into here and it will calculate Fibonacci 1, and then it will go into here, and then since it is 1 less or equal to 1, it's going to return 1. So we know this will be 1, and it will also calculate Fibonacci 0, and Fibonacci 0, 0 less or equal to 1, which will return 0. So we basically know that it's going to return 1. However, in a higher level, for example, form, let's say, it's going to need to calculate this one as Fibonacci 3, which will then go into here and then calculate Fibonacci 2, and then it will go into the function again and calculate Fibonacci 1, which will return 1. And then since we have 1 as Fibonacci 1, we're going to calculate Fibonacci 0 since we're on and 2. And it's going to return 0, and 1 plus 0 will be 1, which will be Fibonacci 2. And for Fibonacci 3, we got Fibonacci 2, so we also calculate Fibonacci 1, and which will return 1 for us. And since we have 1 and 1, we're going to have 2 as Fibonacci 3. Or maybe I should write these in a text file to make it more understandable. If we're calculating Fibonacci 4, we're going to be calculating Fibonacci 3 and then Fibonacci 2 and then Fibonacci 1. And since we, okay, maybe I can also write it like this to say that we're going to into a recursion. So this method calls this one, and then it calls this one, and then it calls this one, but Fibonacci 1 doesn't call anything, so it goes to Fibonacci 0 because we have Fibonacci 1 and then Fibonacci 0 to calculate Fibonacci 2. And since these are going to be calculated, this will be calculated. But to calculate Fibonacci 3, we need to have again Fibonacci 1. And since we have these ones, we're going to have Fibonacci 3 as well. But to get to Fibonacci 4, we need to calculate Fibonacci 2. And that will call Fibonacci 1 and Fibonacci 0 separately. And then we are going to have our Fibonacci 2. And since we have our Fibonacci 3, we add this value and this value to get Fibonacci 4, and then we return to our main code. That's basically how it works. And maybe we could, let me go back to 2, okay, and then maybe I can show the low level and the assembly one. Okay, the low level code is written here, and in assembly also we have our Fibonacci value that we need to calculate, and we are going to the function anyway, so our main code is basically done. Like you can see here, it saves 100 here and it goes to this location when it does this instruction. And this top part is basically the same as this part, and you can see that it actually is. It uses -3, +5, and +4 and whatnot in the code, and you will be able to understand it when you go over these by yourself. And I have already gone over it in the first part of this lab, so I think you should be fine with it. However, in this, hold on, go to skip. Okay. I think what happens in here is this part is inside the if. I'm sorry, I have not checked it entirely, but I'm pretty sure it is because it is calculating stack pointer -1 here and also stack pointer +3 and basically doing this instruction, which is also again here. So this part is basically this part, and it is again going to top. And these parts, they are basically written in assembly already, so you don't need to change those ones. But where it gets interesting is you need to fill these instructions and basically do these ones to make the code work. By the way, you don't really need to fill every single number of these instructions. It could be shorter for you guys. It will change according to how you deal with your code. It could end like 2 instructions previous. And if that happens, you can just also write this instruction where it ends, and also here again you can write it. For example, if it ends in 140, you can do 141 and EZJI. between 90 and 0, it should be fine as long as you do your code and it works. Um, and again, we have a stack pointer here which should be saved, which should save this value. So we know that our stack pointer is 350 and it saves 400 or 403 and so on, since there are three values again. Um, Let me see. You need to be careful about using these. Make sure you don't lose your original pointer, which is here. If you lose it basically in your code, you will basically be lost because it keeps using pointer over and over again. As you can see here, it all gets green. So be careful and make sure you use enough temporary values here to not lose the value that you should have in pointer. Um, yes, I think that's about it for this part. And by the way, these values, the return point 1, return point 2, they should be saved. Yeah, they are saved in these locations. Also, skip and top are also saved in these locations, but you don't really need to change those or use those at all. You can use these temporary values, I think, which tells temporary 0 is also being used here, so you can these values. You can also go up to 399 if you need to. And just a reminder again, you can use these values right here. It's going to make your life a lot more easier because, for example, here you have -2 and here -3, so it's going to be easy on you to use these ones. And again, -1 is not being used in your code, in the code that you need to write. However, it is used here, so it's making all our lives easier. Um, if you need any other minus values, feel free to add it maybe from this address onwards, or there is some other values, it's fine. Yes, I think that's pretty much about it. If you have any other questions, make sure you ask them in the lab sessions. And since we're taking attendance, we expect you guys to be in those sessions. And we are sometimes having quizzes in those lab sessions. So make sure you attend. You are graded on your attendance as well. Um, However, if you don't have the question in the lab session times, feel free to ask them on Piazza or via an email, or maybe even LMS, since we have the chat function there as well. Thank you for watching and listening. I hope to see you in a next lab.